Yes.
Okay. Okay, I think we can start. So next speaker of the session is Kodjo Raphael Madou, and he's going to talk about admissible singular drifts of symmetric alpha stable process. Please.
Thanks for introduction. It's for me a real pleasure to participate to this conference and have opportunity to present this work, which is a result of a collaboration with Professor Damir Kinzi-Bulatov, titled on admissible singular drift of symmetric alpha state process. We start with a recall of the fractional Laplace operator definition given by this formula. Note that is a non-local operator. From the probabilistic point of view, this operator is obtained by subordinating a Brownian motion using an alpha step subordinator. We are going to introduce now the central analytic object of this talk, which is the fractional Kolmogorov operator, is obtained by perturbing the fractional Laplace operator by a gradient field. We are specifically interested in locally unbounded drift. One of the classical problems intensely studied in the literature is the following one. What are the admissible singularity of drift? That is, for which class of drift there is existence of semigroup in L2 C infinity. Then a relationship between the integral property of drift and the regularity of the domain of the Kolmogorov operator. The subject of this presentation is the existence and uniqueness of the weak solution of the following stochastic differential equation for a locally unbounded drift B, where the process ZT be a rotational symmetric alpha state process. Note that this process is generated by the fractional Laplace operator, and IST is the unknown process. The fractional Kolmogorov operator is associated to this stochastic differential equation. This question has taken an important place in the last decade. The very first principal result is due to Portenko in 1994, who considered a drift in the following class and proved the uniqueness in law of the solution of the SDE. We also mentioned his result in collaboration with Podolini, which was in the continuity of the previous result. Sorry. In the other hand, this class is far from being the best possible. Later, more larger class was introduced. It's the Kato class. We will say that a vector phi B belongs to the Kato class that we note here, K delta D alpha minus 1. If for any non-negative delta there exists a non-negative constant lambda such that this estimate is verified. Kato class express smallness of absolute value of B with respect of fractional Laplace operator. Note that this class contains for a given non-negative epsilon certain vector field B such that the absolute value of B is non-locally P integrated with P equal to 1 plus epsilon. Now let's mention some results on STE with drift in Kodjo class. We have Chen Kin Song in 2012, Kim Song in 2014, Chen Zhang in 2017 have considered a drift in Kodjo class and proved the existence and uniqueness of the solution of the STE. This class is recognized as the class responsive for the existence of two-sided estimate on the head kernel of fractional Laplacian operator in terms of the head kernel of the fractional Laplace operator. Now we introduce in this talk a much larger class than Kodjo class, the class of weakly form-bounded vector field defined as follows. That we note here if delta phi minus 1/2. Delta is the form bound. Here again, this class expresses smallness of absolute value of B with respect of fractional Laplace operator. This definition can be described equivalently in the sense of quadratic form. So let's give some few examples. First, consider a vector field belong to Potenko class. By using the fractional Sobolev theorem, we get B belong to the class of weakly form-bounded vector field. Similarly, for B in the weak LD over alpha minus 1 class, we get B in weakly form-bounded vector field class. As an example, also the Hardy drift belong to the class of weakly form-bounded vector field via the Hardy inequality or Hardy relative inequality. As announced on the previous slide, the class of weakly form-bounded vector field contain the Kodjo class as well as Campanato-Mori class. The main result of this talk is as follows. Let B belong to the class of weakly form-bounded vector field with sufficiently small data. First, we have an analytic result. There is a failure generator associated to this fractional Kolmogorov operator on C infinity. So failure generator on C infinity, space of continuous function vanishing at infinity plus some regularity result. And we know that by standard results, the failure semigroup determine probability measures such that the failure semigroup is conservative. We have this estimate where I is expectation associated with the probability measures. This condition is necessary in the construction of the weak solution. There exists a process ZT, which is a symmetric alpha state process under the probability measures, such that ST satisfy the equation. This concerns the existence of the weak solution. Then we have uniqueness. Here we are talking about weaker uniqueness. This means that we can construct another weak solution by this approximation procedure. If you do that, the weaker uniqueness holds. Nevertheless, the uniqueness in law of the solution of SD remain an open problem for a weakly form-bounded drift. We will have to work on a minimal problem and then on a maximal problem. We first have to solve a minimal problem, that of finding the condition on the drift B, which will allow us to construct a realization of the Kolmogorov operator as a generator in L2. Note that the form method is problematic here because we will not be able to control the perturbation term for a drift in this class. We arrive at the condition B belong to the weakly form bounded vector field with delta less than 1. For the maximal problem, it will be a question of finding additional condition on the weakly form bounded vector field, which will allow us to construct a failure semigroup and thus the solution of the SDE. What is amazing here is that the assumption on the drift that satisfy the minimal problem is the same that satisfy the maximal problem with smaller data. We recall the condition who give a vector field in the weakly form bounded vector field, and so the role of delta. Let's begin with the minimal problem, such as the construction of C0 semigroup in L2. We are going to guess the resolvent in L2, the resolvent of the fractional Kolmogorov operator. Here, A is the fractional Laplace operator. Given delta less than 1, we define the operator theta2 with two representations as follows. This operator will become the resolvent of the generator of strongly continuous semigroup. It appears formally as a Neumann series. So the operator H and I's are bounded in L2 for a weakly form bounded drift. We show that theta2 is resolvent by first showing that it's a pseudo-resolvent and then by using Trotter theorem. Then let's talk about the maximal problem. We are going to guess the resolvent in LP. We recall once again that here A is the fractional Laplace operator. We define the operator theta P with this representation. As before in L2, theta P appear formally as a Neumann series. With a weakly form bounded drift, it's required that the operator G, Q, and T are bounded in LP. This operator will become the resolvent of the generator of strongly continuous semigroup, but now in LP. We show that G, T, and Q are bounded in LP, thanks to being the weakly form bounded vector field via LP inequality for symmetric Markov generator of Liskevich-Semenov. We show that the theta P is resolvent by first showing that it's a pseudo-resolvent, and then by using Trotter theorem, this time in LP. Let us recall again the representation of the operator theta P and put in relief the regularization term colored in blue in the above representation. By Sobolev and Bending, we show that the domain of the operator is contained in this Bessel potential space. For a sufficiently large P, then the Sobolev send us into C infinity. In particular, for P greater than D minus alpha plus 1 by the Sobolev embedding theorem, we find that the operator theta P is contained in this intersection where C0 gamma represents the space of Holder continuous space. An extension of the resultant can be defined on the intersection of C infinity and LP, and so by applying once again to Trotter theorem, now in C infinity, we arrive at our failure semigroup. So by failure generator, yes. And so on in failure semigroup. Back to the SDE, we know that by standard result, the conservative failure semigroup determine probability measures such that we have this equation. We will use a weighted variant of LP of an argument in Potenko and Podolini to show that the corresponding probability measures give us a weak solution to the SDE. We'll show that the process T is an alpha state symmetric process by analyzing this function. We can list other results dedicated to the study of SDE with singular drift. First, in the local case where alpha is equal to 2, the corresponding result on the existence and uniqueness of a solution has been obtained recently by Kinzibuletov and Selinov. We also mention a series of papers by Nikolai Krylov, who consider a drift in LD or LD plus 1. Krylov and Rottner improve strong solution of SD with singular time-dependent drift. Zhang, who shows strong solution of diffusion stochastic equation with singular drift. And recently we have a result of Rottner and Zhao, who show weak plus strong solution of SD with singular time-dependent drift in critical Lebesgue space. This ends my talk. Thank you for your attention.
Thank you for your talk.
Thank you.
Other questions?
Difficult to say. So it's a good result with for a particular operator, class of operators. So can one add a potential to your things and then obtain something? I guess so.
You see?
What about variable coefficients in front of this fractional Laplacian? So if we start not with the Levy process, but with some failure process already. Drift perturbation of something more general than just a fractional Laplacian. For example, fractional Laplacian with variable coefficient in front. Or power of fractional Laplacian is variable.
I did not have explored this way yet.
Yes, it's clear, but it's a kind of suggestion what can be done further. So to say.
I don't know.
Yeah, so it's clear. So I just say that it can be probably done in the future. So one can generalize this approach to consider not just a fractional Laplacian, drift perturbations or fractional Laplacian, but instead of fractional Laplacian to consider, for example, fractional Laplacian with variable coefficient in front of it, or variable power of fractional Laplacian, so that you start already from the failure process.
Okay.
Not LV, but failure.
Okay. I think it will be possible, but the main difficulty will be on the definition of this operator when we introduce the coefficient in the power.
Okay, you don't have to answer it now. So this you can answer it at the next conference,
Yes.
after a couple of years.
Okay, if there are no further questions, then let's talk speaker again.
Thank you.
I think this is the end of the session. So
yes,
we will close it, and then at 2 p.m. UTC, the next main session is starting.
yeah.
So wish everybody a nice afternoon.
Yeah. Have a nice time and see you later.
Okay, thank you.
Bye.
Bye.
Bye.